Good afternoon, folks. Today we're going to be talking about the atmosphere, its circulation patterns, and air-sea interactions. The atmospheric circulation patterns and the atmosphere-sea interactions are extremely important for the ocean dynamics, as we will see very shortly. So we're going to be starting with the solar radiation and heating and cooling of the Earth's surface through solar energy power. Then we're going to look at the structure and composition of the atmosphere very briefly, and we're going to talk about the Coriolis effect, and then we're going to start talking about some of the important air circulation patterns, and we're going to finish up with the monsoon systems in India and in the Indian Ocean. Now, the Earth has two significant energy sources, as we talked about in the beginning of the semester. One is the internal energy coming from the hot core of the Earth that drives the plate tectonics. And the second one is the external energy coming from the sun. And the solar radiation is extremely important for the superficial processes on the face of the Earth. So the Earth's climate is powered by the solar energy, as you well know. And over the course of a year, the Earth system, the land, the continents, the mountains, the oceans, and the atmosphere absorb enormous amount of energy to the tune of about 240 watts of solar power per square meter. This solar energy is extremely important for photosynthesis, done by plants and also in phytoplanktons in the oceans. It fuels the evaporation and precipitation patterns on the face of the Earth and, of course, warms the Earth system. So the Earth's climate, global climate, depends on this solar energy and how it is balanced in terms of how much is absorbed by land, how much is basically reflected back into the atmosphere. So incoming sunlight and outgoing terrestrial radiation from the Earth really affect the climatic patterns on the surface, and to the largest extent they balance out. So if you look at this diagram, you're going to see the incoming solar energy 100%. Part of that is reflected back to the atmosphere. Part of it is reflected by those puffy white clouds, and some of the solar energy is reflected directly back from the Earth's surface. But take a look at this. Solar energy, nearly 50% of it is absorbed by land and the oceans. And then, of course, the solar energy is radiated to space from clouds and the atmosphere, and some of it absorbed by the atmosphere itself. And so there is this basically flow chart of the solar radiation. In the end, these flows pretty much balance out to keep the solar energy fueling the sufficient processes on the face of the Earth. So what causes these kinds of changes in solar radiation patterns on the Earth? There are three significant causes. You know the first one really well, the daytime-nighttime cycle. And then, of course, the seasonal changes. The Earth has a geoid shape, not a perfectly spherical globe. And the Earth is rotating around its tilt axis. And this rotation around the tilt axis basically causes the Earth to have seasons. Latitudinal effects also play a significant role in changes in solar radiation patterns on the Earth. The Earth's atmosphere does not have a uniform thickness. Because of the geoid shape of the Earth, the atmosphere is much thicker over the equatorial zone, about 18 kilometers in thickness, but it is thinner over the poles, about 8 kilometers only. So that's a significant change in atmospheric thickness, and that in turn affects the atmospheric absorption of solar radiation. So the equatorial atmosphere absorbs much more heat coming in from the equatorial from the sun. Albedo effect is another important latitudinal effect. As you know, white ice caps and glaciers near the poles in the Earth reflect that incoming sunlight back into the atmosphere. So there's a high percentage of incident radiation in the polar regions, and that also affects the solar radiation artifact in the polar regions. And finally, you know that ocean surface almost sometimes is as a mirror, reflecting back the ocean, reflecting back the solar light, so solar energy. So the ocean reflects more radiation at high latitudes because of the sunlight coming in to the polar regions at an extremely low angles. So because of that, the solar radiation is lost for this reason at polar regions as well. If you look at the average daily solar radiation values at different latitudes throughout a year, we're going to see some interesting patterns. First of all, let's orient ourselves with respect to this diagram. So along the horizontal axis, you see the seasons: winter, spring, summer, and fall. And the vertical axis is the solar radiation in terms of hundreds of grams per calorie per square centimeters per day. And the equatorial zone here has a very flattened sinus curve, as you can see, and the fluctuations on a seasonal basis are not that important. You see that between the winter and spring and summer, only very few degrees of changes in solar radiation. But if you go towards higher latitudes, both in the northern hemisphere and southern hemisphere, you'll see that the changes are much more dramatic. Look at the green dashed lines showing the changes, seasonal changes of solar radiation in the northern hemisphere. As you go from mid-latitudes, about 30 degrees north, towards 60 degrees north, and then towards the 90 degrees north to the North Pole, you'll realize that the changes, temperature changes, and the solar radiation changes are extremely dramatic. And the peak values of solar radiation at the higher latitudes occur during the summertime, as you can see right here. And the same thing in the southern hemisphere, shown by these red curves. And you'll realize that the 30 degrees south latitude to 60 degrees south latitude, the seasonal solar radiation changes become much more dramatic. So the higher values of solar radiation in the northern hemisphere almost coincide with the lower values in the southern hemisphere. The reason why the northern and southern hemisphere patterns look a little bit different is because, as you remember, this northern hemisphere is mostly continental hemisphere, whereas the southern hemisphere is mostly an ocean hemisphere. So these patterns of solar radiation fluctuations, to the largest extent, part of that major difference between the two latitudes. So heat gained at equatorial latitudes on the face of the Earth quickly dispersed and transferred towards higher latitudes. So heat is gained at near the equatorial zone and lower latitudes, and then lost at higher latitudes. So there's this energy transfer. And the winds and ocean currents redistribute the heat around the Earth. If that didn't happen, equatorial regions would have extremely hot ocean water and extremely cold, in fact, permanently frozen cold water in the polar regions. But that is not the case. That's because winds and ocean currents collectively transfer the heat so that the ocean temperature is actually pretty much stable throughout the year. We will talk about structure of the atmosphere a little bit at this point to better understand how atmosphere functions. So we're looking at a diagram here that shows the height above Earth. And you can look at this also, the thickness of the atmosphere going from the surface of the Earth higher into the sky in terms of kilometers, and the horizontal axis is the temperature in degrees Celsius, going from minus 80 degrees Celsius on the left to plus 20 degrees Celsius on the right hand side. So we have four layers of the atmosphere: the troposphere, stratosphere, mesosphere, and thermosphere, which is the highest layer in the atmosphere, between 90 kilometers and higher up. These different layers, atmospheric layers, are separated by different boundaries: tropopause, separating troposphere from stratosphere; stratopause, and mesopause, the other two boundaries higher up. Yellow curve shows the temperature changes in the atmosphere with height or elevation. So you realize that the troposphere has very high temperatures close to the Earth's surface, but then those temperatures plunge significantly down to nearly minus 60 degrees Celsius as you cross the boundary into the stratosphere. And then after this hairpin turn, the atmosphere warms up again within the stratosphere. The reason for these differences is because we have heat loss from the Earth's surface. So heat conduction is affecting this part of the curve, and then the reason for this quick rise in the temperatures in the stratosphere is because we have the ozone layer within the troposphere, and that ozone layer absorbs the UV radiation, raising the temperatures in the stratosphere. Once we cross into the mesosphere, the air temperatures are decreasing very quickly again. And that's because there is no absorption of solar radiation in the mesosphere, and therefore the mesosphere gets quickly very cold as we go higher up, and then into the thermosphere, the temperatures may rise a little bit, but remain pretty much within minus range, significantly low minus range. Now, all the activities, as we know, in terms of atmospheric circulation patterns and clouds and rainfall, precipitation, evaporation, convective circulation, they all occur within the troposphere. And the jet stream is located near the boundary of the troposphere against the stratosphere. And the ozone layer, as we said earlier, is in the stratosphere. And when you travel by airplanes, usually pilots climb up into 30 to 35,000 feet altitudes, and to basically go over that really bumpy, cloudy part of the troposphere, so that they are cruising in the lower altitudes of the stratosphere to go beyond or above the clouds, and also climb up above the jet stream as much as it's possible. So let's take a look at the composition of the atmosphere, because that's very important for for humans. The atmosphere contains three most significant gas types essential for organisms and life: nitrogen, oxygen, and argon, the argon gas. Collectively, they are making up nearly 99% of the dry air by volume. And then, of course, we have carbon dioxide and water vapor in the atmosphere. Where water vapor might be up to sometimes 4%. And the other gases include neon, helium, methane. Methane is a greenhouse gas, as you know, krypton, and hydrogen. So all these gases in the atmosphere are bound to the Earth by the gravitational forces. And in terms of their distribution within the first 50 miles of the atmosphere close to the surface of the Earth, really don't change much. And because within the first 50 miles, due to strong winds and turbulence, these gases are mixed completely, so fluctuations are very minimal. And the carbon dioxide concentration in the atmosphere is something that we, the scientists, are keeping a close eye on. Because, as you know, carbon dioxide is extremely important for global climate change. And before the Industrial Revolution, the carbon dioxide concentration in the atmosphere was about 280 ppm, and then started increasing because of the anthropogenic effects. And about 1960 was measured at 360 parts per million, and then went up to 395 ppm in mid-2012. That's a significant jump in a matter of basically 50 years. And that number is increasing as well. So that's something that we're going to get into later on when we talk about the role of carbon dioxide in ocean dynamics and also in global climate. We're going to talk about the Coriolis effect next. Coriolis effect is one of the most important phenomena on the face of the Earth, affecting the ocean currents and ocean waves, and also the atmospheric circulation patterns. Keep in mind that we live on a rotating Earth, and so the Earth is rotating around its tilt axis. If you look at the Earth from the North Pole, directly looking down to the Earth, the rotation direction is counterclockwise. But if you look at the Earth from the side, from a distance, with the North Pole at top, you will realize that the Earth is basically going to the right, rotating to the right. Now, as Earth rotates, different latitudes travel at different speeds with respect to that pole of rotation. So here's the tilt axis of the Earth, and the Earth is rotating in this direction to the right, or counterclockwise fashion. And as you go away from this pole of rotation, the speed of any object moving above the Earth is increasing as you get away from that pole of rotation. So you see that these vectors are getting longer with higher magnitudes. At about 30 degree north latitude, 800 kilometers per hour. And then you get to lower latitudes, 1400 kilometers per hour, and so on. So the change in speed with latitude causes what we call the Coriolis effect. Because of this Coriolis effect, the air currents actually bend on the above the Earth. Wind bends winds bend to the right in the northern hemisphere, and they bend to the left in the southern hemisphere. So if you look at this diagram on the right hand side, because of the Coriolis effect, a wind blowing from the equatorial zone towards the mid latitudes will be deflected to the right in the direction of the wind blowing. And if there is a polar jet stream or polar wind coming down from the north towards the mid latitudes in the direction of that motion, again in the northern hemisphere, that particular wind system is going to bend to the right. So, an exactly mirror image of these phenomena in the northern hemisphere down in the southern hemisphere, deflected basically pathways of winds. The same thing as airplanes, not attached to the face of the earth. If a pilot basically is trying to fly from New Orleans to Chicago, further north, has to make sure that that he or she considers the Coriolis effect, because it's the airplane is not going to be flying on a straight path, but it's going to be deviating to the right. So the pilot might end up with actually not in Chicago, but farther to the east because of the Coriolis effect. So objects, air, airplanes, and as we'll see later on in ocean currents, they basically move along a curved path, not in a straight path. Although they may look like they're traveling in a straight line. So these arrows show in the northern hemisphere and the southern hemisphere how those objects may be deflecting and veering off from their straight paths of travel. So this Coriolis effect is extremely important for atmospheric circulation in wind belts in the Earth. We're looking at a diagram here, a two-dimensional projection of the Earth. You can consider it as a sort of slice of Earth, North America, South America, the equatorial zone, 30-degree north and south latitudes, and then the North Pole. We talked about the high solar radiation in the equatorial zone, which heats up the air right over the equatorial zone. So the air rises at the equatorial zone, and as it rises, it starts flowing both to the north and to the south in both hemispheres. And it gets deflected to the right in the northern hemisphere and to the left in the northern hemisphere because of the Coriolis effect. So the rising air travels in the atmosphere and then starts sinking at 30-degree north and south latitudes at subtropical highs and moves along the water-covered surface of the Earth, either back towards the equatorial zone here or towards the polar regions. And so we basically have this Hadley cell operating between the equatorial zone and the 30-degree north and south latitudes. And at 60-degree north and south latitudes, here and here, the air rises again because it's getting warmed up and producing the polar jet streams that we're going to be also talking about later on. The air that reaches the polar regions, the North Pole and the South Pole, now becomes very cold and denser, and it sinks and moves towards lower latitudes and warming up and picking up basically water vapor and becoming extremely moist. So these atmospheric circulation patterns affected by solar radiation patterns and the Coriolis effect create three significant airflow cells in the atmosphere. We have the trade winds blowing from the northeast to the southwest in the northern hemisphere and blowing from southeast towards the northwest in the southern hemisphere. And then we have the westerlies. The westerlies flow from west to east, and that's why we call them westerlies, because they're coming from the west. Same in the northern hemisphere and the southern hemisphere. And then we have the polar easterlies, and they're flowing towards the east from the polar regions, and they're extremely, extremely cold. So there are these three different and very significant wind patterns that you have to learn, because we'll see later on that these different wind patterns on the face of the Earth in the atmosphere strongly affect the oceanic current systems. So if the Earth did not have the Coriolis effect, we would not have all these three different wind belt systems in the Earth. We could only have these cells with rising and sinking air masses and no motion of the curved motion of the air masses in the atmosphere. But because of the Coriolis effect and deflection of air masses because of the Coriolis effect, we have easterlies, westerlies, and the polar easterlies operating on the face of the Earth. So one of the most important phenomena in terms of the atmospheric circulation patterns is the jet streams, and you hear so much about jet streams when you watch TV, and the weather patterns. Meteorologists tell us quite often about what the jet streams are doing in our state. Jet streams are fast-flowing, narrow, meandering air currents in the atmosphere. So you see there are two jet streams. One is the polar jet at higher latitudes, and the other one is the subtropical jet at lower latitudes. It is the subtropical jet that strongly affects the climate in Ohio. And it basically goes up and down depending on how the polar jet stream behaves, particularly in the winter times. But notice that these jet streams are not moving along a straight line, but they're actually meandering just like a river and curving along as they circle around the Earth. They're located near the altitude of the tropopause, the boundary between the troposphere and stratosphere, and they're always flowing from west to east. And jet streams may actually start, stop, split into two or more parts, or combine into one stream to become even much stronger. These jet streams are the products of two factors. One is the solar radiation that we talked about, and this solar radiation generates those cells operating in the atmosphere, circulation cells. There are three of them: polar, Farrell, and Hadley circulation cells. And the second one is the Coriolis effect. The Coriolis effect is affecting jet streams operating in the atmosphere as well. So this cross-section shows the relationships between the subtropical jet stream and the polar jet stream. Polar jets are operating at lower altitudes, about 9 to 10 kilometers, about 60-degree north and south latitudes. And the subtropical jets are operating between between 20° north and south latitudes and over the equatorial zone, and they're operating at a much higher altitude, about 10 to 16 kilometers above sea level. So the subtropical jet stream is part of the Hadley cell, as you can see here, and the polar jet stream is part of the Ferrel cell. And polar jet is extremely cold because of the cold, dry air at these altitudes, and and the subtropical jets are extremely moist and bring lots of rain and precipitation. These both jet streams have extremely high velocities, 75 meters per second to 125 per second average speed of these jet streams. Let's take a look at air masses in North America. We have 7 air masses, 8 air masses actually, and some of them generated over the land, and some of them are generated over the oceans, but both affecting the climate, particularly on the continents, but also in the oceans as well. So we have the continental Arctic air mass originating and usually sitting on top of the near the North Pole, very cold, very dry, and the continental polar air mass shifted to the south a little bit and over the Hudson Bay and getting close to the Great Lakes. And this is also very cold and dry air mass. Then we have the maritime polar air mass originated over the Pacific Ocean, actually over the Asian continent and coming towards the east. This brings cool and very moist air to the continent. The opposite of that is the maritime tropical air mass. It is warm and moist. It's coming from the southwest and picks up lots of moisture and warm air and brings lots of rain and warm air into the Baja California region and New Mexico and Arizona and Southern California as well. And then we have the continental air mass in very southern United States and in Mexico. This is very hot and very dry, and so much of Sonora Desert is overlain by this continental air mass. On the east side of the continent, we have the maritime polar air mass originated from the North Atlantic Ocean and bringing lots of cold air and sometimes also moist as well. And the maritime tropical air mass is the driver for the hurricanes that we experience in the southern United States. Extremely warm and moist air fueled by the warm temperatures over the Atlantic Ocean and near the African continent and migrating to the west and northwest, coming towards the Gulf and southeastern United States. So if you look at the maritime polar air mass a little bit more closely, this cool, moist air mass, again originating on the west side of the Pacific Ocean over the Eastern Asian continent, and it migrates to the east, and it brings heavy rains and very cold air along the west coast of the North American continent. This cross-section shows what happens to the maritime polar air mass as it travels from the Eastern Pacific Ocean over land. So you're looking at here near Washington state, it dumps lots of rainfall on the west side of the Olympic Mountains, and then rises, gets cooler, and then sinks. And now it dumped all the moist that it contained as precipitation over the Olympic Mountains. So it's dry and cold and sinking, and then it picks up some more moisture on the way as it's traveling towards the Cascade Mountains, and there's more precipitation over the Cascade Mountains. And then it sinks again because it's cold and dry, and migrate keeps going to the east, and by the time it reaches the Rocky Mountains, it causes some more precipitation over the Rocky Mountains on the west side, and rising over the Rocky Mountains one more time, it is basically now cool and dry and sinks, and forming that cold air coming towards the Midwestern states. The maritime East Coast cold air mass is not as strong as and stable as the one that we just talked about coming from the Pacific Ocean, but it's much colder than the West Coast maritime pressure system, usually brought onshore by winds and high pressure system to the north of us, and it can also be pushed by the low pressure system from the south. So it is usually located about the northeastern part of United States and southeastern Canada. Let's take a look at the annual range of mid-ocean sea surface temperatures. This diagram shows from north to south a profile along the three oceans, the Atlantic Ocean, the Pacific Ocean, and Indian Ocean, in terms of annual range of sea surface temperatures. So we're looking at basically what happens in these oceans in terms of their sea surface ocean water temperatures in the middle of the oceans, far from the beaches and continental masses. So the temperatures going from 0 to over 10 degrees Celsius on the vertical axis. This is both for continents and for the oceans. And if you look at the land shown by this black curve, you realize that the annual range of surface temperatures on land are maximum at very high latitudes. In the equatorial region, the annual fluctuations are not that important on land, but as you go beyond 20-degree north and south latitudes, immediately you start picking up a significant gradient in the range of temperatures. And if you look at the oceans, the Atlantic Ocean is given by the blue curve, and Pacific by yellow curve, and the pink one is the Indian Ocean curve. You will notice that the Indian Ocean curve is much shorter, and that's because the Indian Ocean is mainly a southern hemisphere ocean, and it doesn't extend into the northern hemisphere, so you don't see this pink curve continuing to the left on this diagram. But one thing that you have to keep in mind when you're looking at this diagram is that the ocean water has a very high heat capacity, and as opposed to the rocks making up the continents, which are poor conductors and they don't have any major heat capacity as a result. And therefore, oceans basically take some time to heat up ocean water, but then they retain that heat for a long period of time. So they don't show as significant fluctuations on a yearly basis and through the latitudes because of that. So if you look at the Atlantic Ocean, you'll realize that the maximum annual range temperatures about middle latitudes. So between 32 to 40, 45 degree north and south latitudes. Both the Pacific Ocean and the Atlantic Ocean show the maximum range of surface temperatures. And Indian Ocean, on the other hand, in the southern hemisphere, also shows the same thing, that at mid-latitudes the temperature fluctuations are very, very important. So the ocean water temperatures, as you can see, affected significantly by latitudinal changes, particularly at the mid-latitudes, but in comparison to the continent's ocean waters, basically have this damping factor because of the high heat capacity. These two diagrams show the pressure cells in the atmosphere, and we have high pressure systems and low pressure systems in the atmosphere, and these atmospheric pressure cells control the direction of the prevailing winds. So we will see later on that these pressure systems control and affect the trade winds, for example, and the westerlies quite significantly. In high pressure systems, air flows outwards and in a clockwise fashion. So you see the blue arrows around the high pressure system. These black lines show the atmospheric pressures in millibars. And so as long as you stay on this particular curve, you are on an same isobar, which is 1020 millibar. So in high pressure systems, the airflow is outwards, upwards, and clockwise, but in the low pressure systems, air flows inwards and counterclockwise. So we have most of the time a high pressure system situated in the eastern Pacific Ocean, and we have a low pressure system residing over southwest United States and northern Mexico in July. And in the wintertime, these pressure systems in the atmosphere change locations. So notice that in the wintertime, we have a low pressure system over the north central Pacific Ocean, a high pressure system in Canada and towards the polar regions, and we have a high pressure system located off the coast of Baja California and Mexico, and a high pressure system in southwestern United States. And these pressure systems affect the climatic fluctuations and changes on land in North America, as well as in other continents as well. Regarding atmospheric circulation patterns, another important circulation pattern is the monsoons. The monsoons represent seasonal reversals in wind patterns over India. So the Indian subcontinent is separated in the north by the Himalaya mountains, which formed only about 45 million years ago. And the Himalaya mountains are almost like a sheer wall extending from only a couple hundred meters to over 8,000 kilometers. And so during the summertime, we have a high pressure system over the Indian Ocean and a low pressure system in warm Indian subcontinent, because the continent is basically heated up much faster throughout the late spring and early summer. So it is now warm, but the Indian Ocean water is still cold. So we have these significant winds blowing from the southwest to the northeast, making up the summer monsoons. This is the case because the winds always blow directly from high pressure systems to low pressure systems. So this Wet monsoon, summer monsoon, brings lots of moisture and dumps lots of rain over the Indian subcontinent. And the Indian culture is dependent on this wet summer monsoon in terms of its agriculture. And once the monsoon winds reach the Himalaya mountains, by that time they rise and they become very cold. And because they dumped all the moisture in terms of monsoon rains in India, they're very cold and dry, and they descend into Tibet. And this is why Tibet is extremely dry and usually cold even in the summer times. In the winter months, the whole scenario changes because now the Indian Ocean water is really warm in comparison to cold land because of the poor conduction of rocks and the fact that the ocean water has higher heat capacity. The continent now is extremely cold and therefore has the high pressure system, and the Indian Ocean has the lower pressure system. So again, there is a wind pattern, wind blow from high pressure to low pressure system. We call this the dry monsoon. And these summer and winter monsoons also affected by the Coriolis effect to some extent. Those of you who spend a little bit time in along the shorelines and beach towns for vacations, particularly in the summertime, have probably noticed that along the shorelines the wind patterns change even during the day, day and night, every day. So during the day, we have very warm land and cold water. So we have this warm air over the land rises because it's now extremely warm and light, and it basically rises into the atmosphere. To replace that rising hot air, cold air moves in from the ocean into the land and brings that very pleasant, nice, relatively cool sea breeze, particularly in late afternoons and early evenings. Later at night, the ocean water now is warmer in comparison to the land, and therefore the ocean water, basically ocean surface, there's this air rising from the warm ocean surface, and the land gets cold at night because there's no sunlight, and so that air sinks and then moves offshore to replace the rising warm air over the ocean surface. So as you can see now, the whole pattern is changed completely around, and so that we now have this basically land breeze blowing from the land into the ocean. And this is why in beach towns or in places along the shorelines, usually later in the evenings and late at night, the temperatures go down dramatically. The last thing I want to talk about is the rain shadow. We talked about this already when we talked about the jet streams. And so rain shadow is basically an artifact of significant topographic changes facing the oceans and continental shorelines. You're looking at the, for example, Andes or the Sierra Nevada mountains or the Cascades as good examples of rain shadow. The moist air coming from the ocean starts climbing over the mountains, and due to condensation we get precipitation from this rising moist air mass, and so that basically we have less of rainfall on the side of the mountains facing the oceans as the air mass climbs over the top of the mountain at high um, altitudes. That air gets colder, and because it lost its moisture, it also is dry, so it is dense and it starts sinking on the other side of the mountains. So this cold and dry air creates what we call a rain shadow with low precipitation and high evaporation. And so the Sierra Nevada mountains in California, one of the best examples of rain shadow effect. That to the west, the coastal mountains in Northern California get less of rain, even in the summertime, as well as in the wintertime. But as you go to the state of Nevada on the east side of the Sierra Nevada mountains, it's a high desert with basically no precipitation at all and significant temperature fluctuations even on a daily basis. So this is all an artifact of what we call rain shadow. The same phenomenon we see in the Andes in South America, and of course, as I mentioned earlier, the Himalayas in Asia also create a rain shadow, an east-west trending rain shadow, so that Tibet is always cold and dry and also very cold temperatures throughout the year. Okay, so this is the end of the air-sea interactions and atmospheric circulation patterns lecture. Next time we're going to talk about the ocean circulation patterns and how these different wind belts that we just talked about may affect the ocean currents. Talk to you soon, and have a good day.